Hi, I'm Antonio Sala, and in this video we are going to continue with the analysis of the force ellipsoid of a planar robotic manipulator, and in particular we'll concentrate on the interpretation of eigenvalue or singular value decomposition of the relevant matrices in the problem. In our example, these were the equations of a 3-link robotic manipulator. The end-effector position was our output of interest, only xy, no orientation, so the manipulator was redundant, non-square Jacobian, and when computing the Jacobian at a particular pose under study, well, we had these numbers, let's say, and this was the inequality defining the force ellipsoid, which is the geometric locus of the feasible end-effector forces in here, which could be counteracted by joint torques in these limits. Well, the exact solution would involve a cube with vertices generated from the limits. The ellipsoid geometry just discusses a normalized torque in the unit sphere, assuming that the physical torque is the normalized one times a diagonal scaling matrix. And we are using the fact that this scale Jacobian transposed times the force gives me the needed joint torque to counteract an end-effector force without robot movement. So this is the force ellipsoid, and with the code you can download, I depicted it with the center at the end-effector position, just for cosmetic reasons, because the axes in this figure have meters as units, but the force has newtons as units. But superimposing everything renders a clearer picture. So what we are going to discuss now is how the eigenvalues of this M matrix and eigenvectors can be interpreted in this ellipsoid, and how this scaled Jacobian singular value decomposition relates to the things we are observing in the figure, what we will call the principal maneuvers. Well, basically from ellipsoid theory, if we carry out the eigenvector-eigenvalue decomposition of this matrix M that defines the ellipsoid, then columns of the V matrix, the eigenvectors, are the semi-axis directions, and the diagonal elements of D are the square inverse of semi-axis length. So this is kind of, ellipsoid theory, independent on whatever developments led me to this M matrix. Let us now discuss the singular value of the scaled Jacobian. I didn't put scaled in the text that you're looking at, because everything is scaled, so just don't forget it, but we are not putting scaled subindices in all expressions. So this force ellipsoid with the scaled Jacobian and it's transposed, well, let us imagine that such scaled Jacobian has this singular value decomposition with the SVD MATLAB command. Then the M matrix defining the force ellipsoid will be with JJ transposed. We have this expression, and as V transposed is the inverse of V because V is an orthogonal matrix, then they cancel out. And so this S transposed is a diagonal matrix, and in fact it contains the eigenvalues of M, because orthogonal, diagonal, orthogonal transposed is the eigenvalue, eigenvector decomposition. So U are the eigenvectors of M, and S transposed are the eigenvalues of M, and the square root of such eigenvalues are the singular values in S, of course. So the columns of matrix U tell me the direction of the principal axis of the force ellipsoid, and the singular values are the inverse of the semi-axis length for principal forces, let's say. The semi-axis of the force ellipsoid have newtons as units, so singular values have inverse newtons as units. So well, somehow this is it. SVD and ellipsoid geometry are deeply linked, and in this particular problem, the link is in the way we just have explained. So in order to better understand what we are saying, let us consider the particular numerical example in the pose we are depicting here. So we have a large force and a small force, whatever, and that will have relationship with the singular values of the scale Jacobian I computed here. So let us have a look at the singular value decomposition of said scale Jacobian. Here we have some U force, S force, V force. Scale Jacobian is 2 times 3. In the force ellipsoid, it was the transposed who appeared in here, but okay, transposing is just swapping V and U. So we can still understand the interpretation of what we are obtaining here as follows. The columns of U are the principal force directions, i.e. semi-axis directions. The columns of V are the principal torque directions. They cannot be seen in the figure of the force ellipsoid because it has force units, but we'll discuss in a minute the meaning. And these singular values have units of inverse length of semi-axis, inverse forces, Newton minus 1. So the actual force units in newtons are the ones in here in which I inverted the singular values. So the force ellipsoid will have a semi-axis of 9 newtons of length in this direction. This will be the high force maneuver, sort of pointing up and a little bit right. Here we have it, the large force of length 9 in this 0.2, 0.9 direction, and we'll have a much smaller force, 0.4 newtons, in this direction here, which is perpendicular to the other one, which is the one here. We can see that this scale Jacobian has a condition number of 20, which means that we can counteract 20 times more force in one direction than in the perpendicular one. This ill-conditioned stuff usually appears when we are close to singularities, as in this case. And now we are in conditions of understanding the meaning of the V matrix, these principal torque directions. This means that, for instance, when I apply this torque at joints 1, 2 and 3, then I will exert 9 newtons of force in the end-effector in this output force direction. When I apply this torque in each of the joints, which has norm 1 in scaled units, so somehow I cannot apply a larger torque, then I will exert 0.4 newtons in this second output direction given by this column of U, and this column corresponds to the null maneuver, so that if I apply that joint torques, I would exert zero force to the end effector and my robot will accelerate in the null maneuver. So it's kind of exerting zero force and moving my elbow, whatever, without moving the end effector. Of course, if our problem statement is that we should compensate an end effector force in order to avoid robot motion, then I should not apply a torque in this null direction. Well, this is what the SVD tells me. So, with this SVD, we are able to analyze the so-called principal maneuvers regarding how to counteract a given end effector force. However, before finishing, let us briefly discuss just a cosmetic change in order to avoid computing singular values and then inverting them to interpret stuff. Indeed, the pseudo-inverse of a matrix has the same singular values but inverted. So, if instead of doing SVD of the Jacobian, we do SVD of the pseudo-inverse of the Jacobian transposed, then pseudo-inverse swaps U and V and inverts singular values. Transposed swaps U and V again, so we get the same U and V as we had here if we were happy with their interpretation, but instead of having these singular values, then we have already the inverted ones. Here we see that this appears here and this appears here, because of course, as SVD sorts the singular values from largest to smallest, then the order is swapped, but it's exactly the same matrices. We'll check in a minute. So the thing is that the interpretation, let's say, is the one we did just a couple of minutes ago. This highlighted blue line is just a cosmetic way of getting the same interpretation with one line of MATLAB instead of two. But it is not that important, let's say. The thing is that in here we have our principal forces of 9.3 here, and if we see, for instance, the principal maneuver with the large force, then we have 0.2, 0.9. Well, it changed the sign because of numerical issues, but okay, it's the same direction of the semi-axis, but instead of pointing up, in here it points down, but it has exactly the same meaning. And this 0.2, 0.98 is exactly the same that we had in our earlier discussion. And of course, this column of V, 0.25 minus 0.7, 0.65, is exactly the same as we see here, but of course with change sign, because if it changes the sign of U, it must change sign of V to keep the gain being positive. So the thing is that with this pseudo-inverse, we get the force directions, we get the joint torque principal directions, and the principal force magnitudes in the same SVD decomposition instead of the inverse force we got before. But okay, as I said, this is cosmetic, so we end the video here. Just summarizing that in this video we discussed the relationship of this force ellipsoid with the singular value decomposition of the scale Jacobian, so we could identify the principal maneuvers and the interpretation. We had two principal maneuvers, maximum force, minimum force, and we had also a null maneuver because in this example my manipulator was redundant. So this is it. Thanks for watching.